Yaskawa.
Welcome to Yaskawa America's e-learning module, Z1000 Features and Benefits. Hello, my name is Paul Avery and I'm an engineer at Yaskawa America Incorporated. I will be your instructor today as we go through this e-learning module covering the Z1000 drive features and benefits. In this e-learning module, we will be discussing features for both the standalone Z1000 drive and the Z1000 in a standard bypass package. We will start by discussing the standalone drive only offering, and then transition into the features and benefits of the Z1000 bypass. The standalone Z1000 product is available in sizes up to 100 horsepower in a NEMA 1 enclosure for the 208 volt AC rating. For the 480 volt AC version, the all NEMA 1 enclosed drives are available up to 250 horsepower. All standalone Z1000 drives feature output amp ratings that match NEC horsepower ratings. For example, at 208 volts, NEC rates 15 horsepower at 21 amps, and the 15 horsepower 208 volt Z1000 output current matches that. The same thing at 480 volts. NEC rates 50 horsepower at 65 amps, and the 50 horsepower 480 volt Z1000 carries an output current rating of 65 amps. Consistent throughout the Z1000 ratings is the fact that the input amps of the Z1000 also match the NEC ratings, which will assure installers that input and output wiring gauges will be consistent. Out of the box, all Z1000s will have 5 kHz carrier frequencies for quiet motor operation. Higher carrier frequencies are available with a current D rate. An exciting addition to the Z1000 is a dynamic noise reduction function that will lower motor noise during low load operation by automatically reducing the output voltage, which reduces the motor noise. The standard keypad for the Z1000 will be a hand-off auto or HOA keypad, similar to the previous generation HVAC Yaskawa drive, but with a different look but similar functionality. This chart presents the amp ratings for the 480 volt version of the standalone Z1000. Note that the CIMR part number is based on the NEC rated output amps of each drive size. The 40 horse Z1000 is rated at 52 amps and the part number is CIMR-ZU4A0052 FAA. The 208 volt version of the Z1000 is shown here, and it should be noted that the 208 version is perfectly fine to be run at 240 volts. Since 208 volt operation requires higher current, the drive current rating is based on the NEC 208 volt ratings. All sizes of the Z1000 include 5% line impedance that greatly reduces current distortion and thus total harmonic distortion at the input to the drive. This makes the Z1000 perfect out of the box for adding to your existing circuit. The drive features an industry-standard RFI filter built to the 61800-3 Category 2 specification as laid out by the IEC. It meets all pertinent FCC standards as well. Yaskawa includes a real-time clock in the Z1000. This real-time clock can be coupled with internal timer functions so that the Z1000 all by itself can run on Monday evening but stop at a particular time on Tuesday, and then repeat for the rest of the week. Because of the real-time clock, fault log events can be stamped with date and time, making troubleshooting easier. The Z1000 has 3 user-programmed 2 amp relays and 1 dedicated 2 amp fault output. By increasing the output ratings to a full 2 amps, new possibilities become realities, as we will see in some later slides. The Z1000 also includes 2 user-programmed analog outputs, both of which can be either 0 to 10 volts DC or 4 to 20 milliamp. The outputs are perfect for providing real-time feedback about drive conditions such as output speed and motor current. The Z1000 is certified by the BACnet testing laboratories and offers built-in BACnet capabilities featuring Instance ID. The Z1000 has the ability to regulate a process through its built-in PI loop capabilities. A secondary and independent PI loop can be controlled by the Z1000 as well. While the drive on one hand is regulating pressure by controlling motor speed, it can simultaneously be controlling a valve's position by controlling the valve with its own analog output, either 0 to 10 volts or 4 to 20 milliamps. The Z1000 will carry the IBC seismic certification in both the standalone and bypass offering. Since the Z1000 is specifically designed for HVAC applications, the drive offers programming macros that pre-configure certain programming points to meet specific application needs, such as typical ramp rates for a cooling tower fan that would be different than the default ramp rates that a pump might use. Anything that gets you closer to final operation with minimal effort is a good thing. Included in the Z1000 is a power supply rated at 24 volts DC and able to supply up to 150 milliamps of current. This is typically more than enough for customer use for powering transducers and transmitters and eliminates the need for a third-party power source. The total Z1000 package is RoHS compliant as well. The largest sizes of the standalone Z1000 come only as open chassis IP00 enclosures. These larger sizes still offer NEC-rated input and output current ratings, the dynamic noise reduction function for quiet motors, and the hand-off auto keypad. Unlike the rest of the Z1000 standalone range, however, the larger sizes are set for 2 kHz carrier frequency, have a 3% bus reactor, and do not feature the built-in RFI filters. Next, we will cover what the standalone Z1000 can do with its internal bypass style logic that will make those integrating the Z1000 into their own bypass package glad that they did. We will go over the standalone Z1000's internal bypass logic by using a timing diagram and showing the state of digital inputs, relay outputs, and the keypad. Note that we are using the Z1000's 2 amp capable relay outputs to switch power to independent contactor coils, which explains why the outputs are now rated up to 2 amps. To start with, we currently have a run command wired into the Z1000's S1 forward run command input. We have 2 normally closed customer safety inputs wired to the S3 input that has been programmed as a drive enable / customer safety input. The S4 input is programmed to be an override input, S5 is a drive select input, and S6 is a bypass select. Inputs S2 and S7 are grayed out because they are not being used in this example. Our M1, M2 relay output will switch power to the drive output contactor, and the M3, M4 relay output will switch power to the K3 bypass contactor. Let's begin. First, to make the keypad easier to view on your screen, let's just show the LCD display and the status of the auto key's green LED. To start this example out, first we have to close the input switch to the drive and press the auto button, giving us the flashing green light to show we are in an auto mode. We are not running yet because the run input to S1 is not closed, and the keypad is telling us that it is in a wait for run state. Had we not pressed the auto key yet, then the message would have said drive off, and the green auto LED would have been off. Note that since we are in the auto mode but waiting for a run, the Z1000 has already closed the M1, M2 output, so that the drive output contactor will close in anticipation of the run command. Once the Z1000 sees the closed run input at S1, it will change its keypad message to run drive and start to accelerate its output. The LED on the auto key stops the slow flashing and stays on steady now that the drive is running. At this point we are still accelerating and the keypad has updated U102, the output frequency monitor, and U103, the output current monitor. We have finally reached the commanded speed and everything shows normal drive operation. At this point, the operator or system controller has decided to switch from drive operation over to bypass operation by toggling the S5 input off and switching the S6 input on. As part of the switchover from drive to bypass operation, the Z1000 will ramp the motor down to 0 using the currently commanded deceleration rate. Until we reach 0, we will remain in a run drive state. Finally, we reach the 0 speed and the K2 contactor is unpowered and the K3 contactor is switched on. The keypad shows that we are now in a run bypass state, and the U102 and U103 drive-specific monitors show 0. We are still in run bypass mode, and the keypad still reflects the last commanded drive speed, though the actual current motor speed is actually 60 Hz. If we drop the forward run command at the S1 input, the drive will open the M3, M4 output, which causes the bypass contactor K3 to open and the motor to coast to a stop. The auto LED stays lit, but is now doing a slow flash. The keypad shows that the bypass select is still the selected state, but that it lacks the run command necessary for motor operation. Next, we will show how the standalone Z1000 can be integrated with a customer's safety circuit. We start with the drive lacking a run command and not even in the auto state. Once we press the auto button and close the S1 input, you can see us once again begin to accelerate our motor up towards our set speed of 45 Hz. Once again, we can view the progress of our operation by noting the U102 and U103 drive monitors. As a new twist, rather than remove the run or toggle from drive to bypass, we've opened one of our normally closed customer safeties. Opening the safety immediately causes the Z1000 to open the M1, M2 digital output, which disconnects the drive from the motor. The motor is now coasting towards 0 and our keypad shows that a safety has opened and the auto LED goes back to flashing green. If during the time the safety is open, the drive select and bypass select toggle, the keypad will reflect that this operation has now switched to bypass, but that an open safety is preventing any motor operation. At this point, we toggle the drive select and bypass select again, but it still can't run due to our still tripped customer safety input. Our auto LED is still flashing. Once the customer safety recloses, the Z1000 will again close M1, M2 and begin turning the motor. The auto LED is now a steady lit green. Finally, things are back to normal with K2 closed and the Z1000 ramping our motor back to our previous reference speed. It should be noted that the Z1000 will offer the same ability to power the control section of the Z1000 off of a 24-volt power supply that Yaskawa offers with its V1000 and A1000 drives. An optional 24-volt adapter connects to the side of the Z1000 and is wired to a customer-supplied 24-volt power supply. In the event of some hardware problems, the Z1000 could operate its output logic while running from the 24 volts DC power. Everything shown about the standalone Z1000 bypass operation could be controlled via serial communication, such as Modbus or BACnet. We mentioned the customer safety inputs, but the Z1000 also offers damper control even when it's just a standalone drive. The standalone Z1000 has a digital input function that will not allow a run unless the building automation system, or BAS, signals that it is okay. Using this BAS interlock, we can set up the Z1000 for damper control using one of its 3 Form A programmable relay outputs. Once a run command is given, the damper control relay output will close and an interlock message will be displayed on the keypad. Once the damper is fully open, the BAS interlock input will close, the interlock message will disappear, and the drive will start to accelerate. The drive will also offer an emergency override function that will allow the drive to ignore customer safety inputs, BAS interlock inputs, and thermal protection inputs, and run at a preset speed for as long as the emergency override input is closed. The Z1000 can also be set up to automatically close the K3 contact in the event of its own drive fault, assuring continuous operation. Now let's transition from discussing the standalone Z1000 to talking about the Z1000 bypass. The NEMA 1 Z1000 bypass package is available up through 150 horsepower in the 208 volt and up through 500 horsepower in the 480 volt package. The bypass includes 2 contactors, one for the drive output and one for bypass. The package is rated for 100,000 amps interrupting current and offers as standard a non-fused disconnect switch. The customer will have to provide fusing worthy of 100,000 AIC separately from the Z1000 bypass. Operation and programming of the bypass will be with a single HOA keypad that will relocate from the drive cube and be installed in the middle of the bypass enclosure cover plate, placing it more at eye level for most bypass installations. The bypass interface board will have as standard a run input, a customer safety input, a BAS interlock, a remote transfer to bypass input, and a smoke purge input. Beyond the standard digital inputs, there will be 3 digital inputs that the user can customize for their own application, and 4 Form C relay outputs that can also be programmed to match the user's needs. All functionality of the Z1000 bypass operation is accessible via serial communications, meaning that BACnet or Modbus or any of the other serial communication options can implement functions like smoke purge. The Z1000 bypass will monitor the incoming power levels and open the contactors in the event that the voltage levels drop low enough to cause contactor chatter or eventual coil burnout. Built into the Z1000 bypass are output CTs or current transformers that will provide real-time current information even when the bypass is running in the bypass mode. Because we can always determine the motor's current draw, the Z1000 bypass will be able to offer broken belt and broken coupling detection even when the motor is across the line. Another neat new feature is the duct pressurization operation that Yaskawa calls pre-run. It will allow the bypass to run a specified low speed while waiting for outside air dampers to open, and then release to full operation after an input closes or a time elapses. This will make integration into a customer's existing applications even more seamless. In order for the operator to easily ascertain the current state of the bypass operation, a new keypad style will offer a whole slew of messages that do just that. Though not an exhaustive list, this slide shows keypad text for the following bypass operational states: running in VFD mode, performing a pre-run operation, waiting for a BAS interlock input to close, running in bypass mode, performing a smoke purge operation using the VFD for motor operation, performing a smoke purge operation using the bypass circuit for motor operation, running in bypass due to an automatic transfer to bypass due to a VFD fault, and running in bypass due to a closed remote transfer input. The Z1000 bypass will come in 3 different NEMA 1 configurations based on size. Up through 25 horsepower 208 volt and 60 horsepower 480 volt, it will be an over-under wall mount style. For intermediate sizes ranging up to 75 horsepower 208 volt and 150 horsepower 480 volt, the standard wall mount enclosure will be used. For the largest sizes, such as above 100 horsepower 208 volt and above 200 horsepower 480 volt, the floor-mounted or freestanding enclosure is used. The Z1000 bypass will feature some important optional add-ons. The standard input disconnect switch can be replaced with either a 65K or 100K rated circuit breaker, removing the need in some cases for customer-supplied fusing. An optional drive input service switch will allow removing power to the Z1000 drive while not interrupting current to the motor via the bypass circuit. An upgrade to a full 3-contactor bypass is possible via an optional purchase. Yaskawa is always happy to provide custom nameplates for their bypasses. Lawnworks, Metasys, and Apogee FLN are available communication options for the V1000 bypass, with the Metasys and Apogee options being no-cost adders. There is a charge to install the optional Lawnworks communication board. Despite the continued popularity of the bypass configuration, there are those who question its benefits. Have you ever been asked, or even thought to yourself, if modern VFDs are so reliable, what is the benefit to the bypass circuit? Or, why spend the money on the bypass equipment if in reality it never gets used? Or even, is there a way that having the bypass operation option can increase my energy savings somehow? Well, the answer to all of these questions is Yaskawa's new IQ bypass technology. The question of investing in the bypass has never been a more obvious yes. Yaskawa's IQ bypass function will automatically transfer from VFD operation to a cross-the-line bypass operation whenever the motor speed reaches a user-selectable speed that is close to 60 Hz. Often during summer months, peak demand will have fans operating at or near maximum speed for hours on end. Most energy savings that comes from using a VFD on a variable torque application like a fan or a pump comes when the speed is low, so the VFD is no longer offering much benefit at max speed. By automatically transferring to pure 60 Hz power, the energy losses of the VFD are removed and the harmonic component of the power consumption is reduced. Reducing the harmonics helps by reducing the heating in the already hot system conductors. When demand drops and the speed needs to be reduced, IQ bypass will switch back to VFD operation automatically and slow the application down. The Z1000 is a leap forward in performance by the company already known for industry-leading quality. With the Z1000 bypass, you get built-in 5% line impedance, built-in RFI filter, and a real-time clock, all in a slim package. Z1000 has BACnet certification as standard and offers a one-of-a-kind energy savings technology with its IQ bypass feature. There is much more to the Z1000 than I can cover in a single e-learning module, so we invite you to explore the Z1000 product at Yaskawa America's corporate homepage by clicking the words yaskawa.com. Thanks again for joining me for another Yaskawa e-learning module. I hope that the time used to review this information was well spent. Please feel free to contact the Technical Training Services Group of Yaskawa America with any and all comments and questions. We would genuinely enjoy hearing from you. Thank you and have a great day.